it didn't work. And what? And sharing. Okay. Okay. No. Still not working. Is it sharing?
Oggi mi sa che non lo c'è. Però mi piace il fatto che sorride ad ogni problema.
No, the interesting thing is that PowerPoint screen has disappeared completely. So lecture, Teams, power supply. There is no PowerPoint. That's it. Ah, okay. So that's the presentation. So it's sharing the second window. Okay. No, how is that? Presentation dove? Sorry. Posso decretare che non è una giornata. Dov'è che si vede questa cosa? È totalmente impallato. Sorry for from home. No, because it's sharing the other. Okay, let's take it. Okay. Allora, set the phone. È praticamente andata. Tre quarti d'ora ci vogliono. Ok, let me do this. Teams, ok, where is this? I kill PowerPoint first. And see what happens. Completamente. Oddio. Sorry. Sapete dove che si settano i parametri sulla presentazione? Questo design,
Professore, ma in caso può usare la versione PDF, no?
No, ok, no, il problema è not PowerPoint, ha settato l'altro schermo. C'è qualcuno che ha smanettato pesantemente col proiettore, secondo me, oggi. Switch Windows. Last but adesso vediamo un secondo. Se ci riesco in 2 secondi, se no niente. Cioè come dicevo. Ok. No, io non voglio questo.
Non lo so che non ha.
Ok. Let me see if. Monta sull'altra. C'è un'altra presentazione. Allora, il problema è che commuta sull'altra schermata, mentre gli vorrei dire di usare, non andare in modalità presentazione, in modalità normale. Come si faceva? Slideshow. No, vorrei più. Mi sta mostrando l'altra schermata. Ok. Okay, we are approaching the solution. Okay. Are you still there? Let's see. Ok, vedete la stessa cosa. Ok. Sorry for this strange way to do it, but if it works, it's fine. So this probably now we start. Okay, so this was the last picture that we saw yesterday, I hope. Or to be true, this was the last picture that I showed you. And that was the so-called fallback circuit. The fallback circuit is something that is a bit different from the constant current short circuit protection. I go back to the constant current. In the constant current, the trick is to use a sense resistor in series with the output current and use this sense resistor for creating a threshold voltage linked to the threshold current that activates the transistor Q-sense. So if the product IL times R sense is greater than 0.6 volts, that is written somewhere, I don't remember here, the transistor activates Q-sense and so takes some of the current that usually goes into the base of the Darlington that we have here. And so this is enough for limiting the output current to a threshold value that we decided here. What I told you is that we don't like, for instance, the fact that when the system is short-circuited, so if we have a short circuit at the output, we still have a threshold current and the total dissipation on the series transistor, on this transistor, is given by the product Vin times the short circuit current, the threshold current. So it's this big area in blue. So it's a large dissipation. Now we see a different circuit where we can limit the short circuit power dissipated in the series transistor. And that is what we called yesterday the fallback circuit. So first of all, we have a look at how it works. Don't consider at the moment this blue area here, okay? So just consider the green line that represents the output voltage as a function of the output current, I. This is a strange function because if you see, it's a function where here, okay, you have a single value for each current, but starting from ISC, you have a function with two possible values for a single current. And it is not easy to describe in terms of how it works. It's kind of, I don't know, S function. You know, we are used to one value function, a function that have only one possible value for each value of the independent variable. Here we have two possible values. So the way to consider this situation is to consider the load resistance. That is this red line, dashed red line. What happens if we change the load resistance? If we have no load resistance, we have an infinite resistance that corresponds to a vertical line, basically a line that starts from 0 and is vertical. So we simply have output voltage VO with no current. Then we start applying a load resistance, and we decrease the value of the resistance. So we can describe the situation with a line that is centered on the 0, 0 point and is bending downside. So this is a resistance which gives the same output voltage, so the system is still working, with this value of current. But if we increase too much the resistance, we decrease, sorry, too much the resistance, because we are increasing the current taken by the power supply, we'll end up with this situation here. You see, with this second red line, the sense resistor transistor is activated. Don't panic. Okay. Now it's switching on and off. Sorry. I'm talking to the PC. So in this situation here, what happened is that the sensor transistor has already been activated. The output voltage is reduced, but also the output current is lower than the threshold current. If we reduce more the load resistance, you see that the output voltage is going down, but also the output current is reduced. So we are working here. When we have a perfect short circuit, the output voltage will be 0, but the short circuit current will be this value that has been further reduced. So it's interesting because basically when we have a perfect short circuit, even if we decided to have a high threshold current, we have a much lower power dissipation in the transistor. The power dissipation, again, is given by the input voltage Vin times the short circuit current. So that's the power that is being dissipated on the series transistor in this moment, which is much less than the other situation where you have the big rectangle here. How can we do that? I can tell you that the basic point is to introduce a sort of positive feedback. It's a masked positive feedback in this system. The point is this one. In the past, we connected the Q-sense with the base on the transistor output, the series transistor output, and the emitter on the load. Here, we still keep the emitter on the load. While we connect the base of the transistor on this voltage divider. The voltage divider is connected here, basically, on the output of on the emitter of the transistor. Okay. How can we explain what happens? Again, we can write a formula on how things go. Basically, in short words, if we have a low current, the R sense and the voltage across F1 are not enough to activate the transistor. If we increase the current, the IL current, we will reach a point where we get to the threshold current voltage. Once we are the threshold voltage, what we can imagine is basically that we have a certain voltage across R sense. Now, basically, if we try to get more current, probably the system will try to reduce a bit the voltage, if it works. So I can imagine that there is a voltage reduction at the output. But a voltage reduction at the output, if we consider at the beginning more or less a fixed current, similar to the threshold, means a voltage reduction at the emitter of the series transistor. Okay, so the output voltage is starting to be reduced, but also the emitter voltage of the Q2 is starting to be reduced. For a given reduction in the output voltage, the reduction in the base voltage is less because we have this voltage divider. And so not only the absolute voltage is divided, but also the variations. So we can imagine, in short words, that we have a certain reduction in the output voltage. The reduction is more or less the same on this node here, but on the base, the reduction is reduced. This means that actually, when the output voltage decreases, the base to emitter voltage is increased. Because base to emitter voltage is given by, this transistor is connected between 2 points where one has the full reduction of the output voltage, the other one has a partial reduction of the voltage. That induces a positive feedback in some way. So the total result is that the system, the lower the output voltage, the higher the reduction, the higher the VB voltage of Q-sense, And so the higher the quantity of current that Q-sense takes from the base of this Darlington transistor. The result is that we are forcing a reduction in the output current. It's strange, but works. Okay. Now we would like to have some formulas for designing the system. Which are the formulas? Well, first of all, we can consider what happens in normal operation of the system. In the normal operation of the system, I can calculate the VBE of this transistor Q-sense. How can I calculate it? Well, it's a bit tricky. Let's see if we can do that. The output voltage is given by V output plus the voltage drop across R sense, that is IL times R sense. And so now this quantity here is the voltage on the emitter of the series transistor. Do you agree? So the output plus the voltage drop across the R sense, IL, R sense. We are here. Then I have to apply the voltage divider, that is RF2 over RF1 plus RF2. And we get the voltage on the base, minus the output voltage gives the VB voltage of this transistor. Okay? So hopefully the formula is correct. I'm not sure, but it should be correct. That's good. It works all the time. If we want to decide what is the threshold current for activating the fallback protection circuit, we must write here 0.6 volts and try to fix also the threshold current, I threshold, and so we can derive, depending on the output voltage that we are choosing, we can select a couple of resistors which activate the sense transistor when we reach the threshold current at the output voltage. So obviously we have an infinite combination of values, RF1 and RF2. So we must choose the values that we like better. We can do some consideration on the current flowing here. For instance, the base current of this transistor must be negligible if compared to the current through the voltage divider and things like that. So we can invent some other criteria for deciding choosing the resistances. So that's the first possibility. The second possibility is to fix, because now we have been working on this point. There is a second point, that is this short circuit condition. When we have the short circuit, we want a maximum current that is ISC. So again, I still have the transistor Q-sense with 0.6 or a bit more voltage on VB. The increase actually in VB is negligible. A small increase in VB is able to increase a lot the current, the collector current of this transistor. So what are the conditions now? And there is a mistake again. Basically, we are using a null V output. So this term here must be killed as well. So I should remove this term here, that is 0. Okay. So what is left is only ISC R sense, but I have already decided all the resistances here. This one. So basically, I can fix the ISC. Those resistances are already decided. Probably I still have to decide the value for that R sense. Okay, but I can decide to use something which is not going to give a large voltage drop, for instance. Usually, those R sense are of the order of 1 or less than 1 ohm, a fraction of ohms. Okay. So using those two relationships, I should be able at least to fix the first and the second point. Actually, the shape of this curve probably is not a perfect line. It's something more complicated. But what we are interested in is that we can activate the threshold current at a certain point, and that we decide what is the short circuit current. the most dangerous situation is when we have a short circuit. So if I'm able to decide the short circuit current, I can decide what is the power dissipation in this situation here. The power dissipated in this situation is useful for designing the worst case, let's say, heat sink for the device. Because our system usually should be able to withstand a short circuit for an infinite time. So after we design the whole circuit, we verify that if we keep in short circuit the system for an infinite time, the system is able to dissipate enough power. Okay. I hope the next days we'll be able to simulate some of those circuits also. So what I would like to give you is a sort of list of possible problems, and so you try to design. If we didn't say something about how to design, you can invent your version, let's say, and then you can simulate and see if it works or not. And then we can discuss on your choices if they were right or not. Okay, we can do that. Okay, that's another sort of power supply protection circuit. Maybe I should say, I should remind which was the problem before moving to this new circuit. Let me go back a bit to the previous situation. The two circuits that I presented yesterday and today are short circuit protections. Short circuit protection are useful if there is a suspect that your load can die, can be destroyed, can go into short circuit, and you don't want to kill the whole power supply. Also because if you're considering a big power supply, probably the power supply is managing a lot of amps, many volts. So it can be a very powerful power supply, some kilowatts in some cases. Well, destroying a power supply that manages kilowatts probably will give a big blast of fire and so explosions and things. So that's something that we want definitely avoid. How? So these circuits here are mainly focused on not destroying the power supply once the load is already dead. What I'm presenting now instead is what they call a crowbar circuit or over voltage protection. What are over voltage protection? Other situations that can happen are when the system is working fine, but maybe there is a overheating of the transistor, or the series pass transistor, this here. Maybe there was a lightning, something that came into the network, a very big spike of voltage, and the transistor can be killed. One way to die for those transistors is to be short-circuited. So if the series pass transistor is short-circuited, the output voltage will be equal to the input voltage. And this will probably kill your load. Okay, so we must be able to protect also the output equipment, the equipment that we are supplying, using what they call the crowbar circuit, which are able to react when there is a voltage that is over a limit. If there is a voltage over a certain limit, the best thing to do is to short circuit the output. Okay, so first of all, you protect the load. You short circuit, you place a short circuit in parallel with your load, maybe the cell phone, for instance, that you are charging. Then, in some other way, you protect the network, the mains. Otherwise, you will make a big blast again, or fire, and so on. So first, let's see how can we detect over voltage, and what can we do? Well, the system here is quite easy. I have to say a few words. Are you familiar with silicon-controlled rectifiers? Or they are a version of PNP devices, or SCR, as they call them.
Ce ne ha parlato il professore Vitale, li ha chiamati tiristori, ma è la stessa cosa.
Okay, they're similar, okay. That's right. Fortunately, Professor Vitale has already said a few words about this device. Those devices usually were studied in electronic devices when I was young, but it was centuries ago. So. Basically, I don't know if you ever studied in electronic devices, also the PNPN device. It's a sequence of 4 layers, PNPN, that can be translated into a couple of NPN and PNP transistor connected that under certain situation, they can activate. Basically, they make a very nice short circuit. So they are very terrible. I mean, unless you buy them because you want to use them, these PNPN devices can also be created in integrated circuits due to parasitic junction and sequence of junction, and they can be really terrible because they can destroy your chip if something goes wrong. In this case, this is basically a PNPN junction with the PNPN junction is between the anode and the cathode. But if you have the PN sequence, the second end contact starting from the bottom is this gate control here. How it works, basically, this kind of diodes remains open, even if it looks like being polarized in direct direction. We have a positive voltage on top and negative on the bottom. It remains open until we send a 0.6 volt pulse in the NP junction, PN junction that we have at the bottom of this sequence. So for activating this diode, we need 0.6 volts on this junction. Once the SCR is activated, there is no other way to deactivate it than reducing to 0 its anode voltage. So it's something that you can activate, but you cannot deactivate. The only way is to reduce to 0 its voltage. Okay. But we don't care at the moment. What we care is try to detect again an overvoltage in this output voltage. This circuit is placed in parallel to the load, with the load, okay? So we have already here the output. If the series pass transistor is destroyed, we will have an increase in the output voltage. So the circuit is quite simple, but it works. We have a Zener diode that is biased by this bottom resistance here. So VZ and the bottom resistance. So more or less we have a VZ voltage here. If the output minus VZ is larger than 0.6, at the moment I just neglected this R, we will have 0.6 volts on the gate of the SCR, and so the SCR will activate. Okay, the output. If the output minus VZ is higher than 0.6, this means that here we have 0.6 or more, and so we activate the SCR. This means that, for instance, if my normal output is 12 volts, but I'm afraid to destroy the load when I reach 15 volts, I will put here a Zener diode of 14 volts, more or less. In normal operation, we have 12 volts that is higher than the Zener voltage. So the Zener diode will be open. But if we have 15 volts, now we are able to have 14 volts on the Zener diode. 15 minus 14 makes 1. 1 is able to activate the SCR. So basically, to be more precise, so if this is 15, that's 14, if it is 14, as soon as the output voltage will reach 14.6, the system will activate. That's the real limit. But in normal operation with 12 volts, the system will never activate. Why did I put, or other people place this R and C resistance and capacitance here? In order to create a low-pass filter, because if for some instances there is a very short spike of voltage, just a noise, the typical motorbike that comes here, makes some noise. This noise could be able to activate this, but first we have a low-pass filter. If there is a low-pass filter is used for filtering very small and short spikes. So the spikes are not able to activate. Only a constant high over voltage will be able to activate the SCR. We can do time constants of the order of 10 milliseconds, something like that. So probably this over voltage is short enough before the system makes the short, so that it's not able to destroy the load. But we must protect the whole system, because once it is activated, you have to switch off everything. Probably you have to change some fuses. Now I'll tell you something. So we prefer not having false activation of the system. Okay. Sì. Okay. It's simpler than that. Simple. Okay. The spike, if the spikes arrive, it takes some time for charging the capacitor. So the capacitor is not instantaneously charged because the spike is filtered by this RC. So it takes some time. So probably the capacitor is not even charged and the spike is already finished. Sì. Quindi praticamente lo spike viene assorbito in termini di carica dal condensatore, che non aumenta più di tanto la sua tensione, e così non ha il tempo di arrivare alla soglia e quindi non scatta. We need a very large voltage increase that has to last for a certain time. Otherwise, the system will not react to these short spikes. If we don't like the fixed threshold, we can change a bit the circuit and move to this circuit here that is one transistor. How it works is quite easy. Basically, again, we have a threshold voltage VZ. Well, we have a VZ zener diode. And the transistor, again, needs a base to emitter voltage larger than 0.6 volts to be activated. So let's do a very simple calculation. What is the base voltage of the system, of the transistor? Be careful. I'm focusing on the base to emitter voltage. So here, I'm not calculating the voltage of the base with reference to ground, but I'm calculating the voltage across RC1. The voltage across RC1 is given by VO RC1 divided by RC1 plus RC2. And that is the voltage over RC1. Okay? Minus VZ gives the VB of this transistor. Only if this voltage, this difference is larger than 0.6, the system will activate. Okay. So this means that if I change the ratio between the two resistances, I can decide what is the threshold voltage. Okay? So probably one of the two, or I will have a potentiometer in between, so I can decide what is the threshold voltage for activating this transistor. Once the transistor is activating, basically it sends a pulse of current to the collector, will charge the capacitor, and will activate the SCR. Okay? Because I'm using a PNP transistor. So I am interested in, you don't see that, okay? It's a PNP transistor, so it's emitter base, and I have to calculate the difference. We can also think this, we have, in normal situation, we have a voltage difference between base and emitter that is below, in modulus, is below 0.6 volt.
But if we have a variation, a strong variation in the input, the strong variation in the input will be at 100% on the emitter, because the zener diode keeps the voltage difference constant. So if we have a plus 5 volt on VO, we have plus 5 volt also on the emitter, while the same increase is reduced by the voltage divider. And this means that, once more, the VB of the transistor is increasing. Maybe it will not increase by 5 volts, but will increase quite a lot. And so we can activate this short circuit, the SCR device. Okay. At least we saved the load, but we are not saving the power supply. Well, the power supply is already half dead, because probably the transistor has died. We still can save, perhaps, the diode rectifiers, the Gretz bridge, or we can save the transformer. That is a lot of money anyway. How can we save the power supply if we have a short circuit at its output? Someone could say that probably the fallback system or the current system was activated. No, because this transistor probably is dead. So we have nothing to do. So we must use something strong, like a normal fuse. Fuses are those devices, very simple devices, where we have a calibrated wire, and the fuse is defined for a certain amount of current. If we overtake that amount of current, the fuses will blow, and we are in troubles. Why we are in trouble? Because we need another fuse, and the shop is closed. So okay, okay. So anyway, first of all, basically, when a fuse blows, it's because there is some hard problem in some part of the circuit. Sometimes it's only because we dropped our metallic pen on the circuit, and so we are in troubles because we know what was the cause of the blowing of the fuse. But some other times there may be some serious damage in the circuit. So the thing to do is just open the circuit and try to check all the devices and see what is the problem. Also, if we find one device that is dead, usually you will never have one single device that dies. But that device died because something else was dead, or that device killed some other parts of the circuit. So most of the time you have to check the whole circuit. No, not so. Here we are talking more than the single wafer. We are talking about a large power supply, where we have, usually if the transistor dies, it will destroy also the bridge, the Gretz bridge, probably. So you have to check all those components before repowering the system. No, it's not. Okay, so, but I want to spend a few words, because fuses are those kind of devices that we know that they exist, but probably you didn't use them. Just to have an idea, if you go to USA, America, let's say all the houses have a box where they have fuses. So if one of your lamps at home just blows, you'll have to buy a new fuse. In our house, it doesn't work like this, because we have a different system. But in USA, they are very familiar with fuses that are that size. They are very large also, because in USA, the mains are at 125 volts, not 220 and 30. So this means that for the same power, you need a double current. All the wires in the wall are much larger. The reason for that is that, in theory, 125 volts can kill less people than 230. In theory, less people. Sono più sicuri, because the voltage is lower. But usually, to be honest, the safe voltage is around 50 volts. That's why all the equipments usually are working, like the telecommunication equipment, are working at 48 volts. That's a standard voltage. Also, if you consider mild hybrid cars, you know, they have battery that is 48 volts. because this tends to be safe. Full hybrid cars have a battery of 200 volts. So, and the same for electric vehicles. They usually have much higher voltages because low voltage means high current. That means a lot of joule dissipation in the wires. That's why we prefer having higher voltage. Higher voltage means less current. Yes. Your colleague is an expert on very high system because you have the Tesla coils and stuff. It makes jump. So he knows that a small wire is enough, but the voltage is very high, so you have to protect in terms of isolation and things like that. Okay, just to try. What I was showing here is that actually when you buy a fuse, you can buy different kind of fuses. The parameter for the fuse usually is the maximum current, but they can behave in different ways. For instance, if you're afraid that as soon as you reach the maximum current, the system has to blow, you will buy fast fuse. The fast fuse blow instantaneously as soon as you reach the maximum level.
Poco prima.
No, appena si raggiunge, o un po' dopo anche, ma poco. While you may be interested in slow fuses, like this T. So why am I interested in slow fuses? Because sometimes after the fuse, I have a capacitor. So if I have to charge a capacitor, there is a spike of current for charging the capacitor, but it's a very short spike of current. So in this case, the fuse waits some time before blowing. Actually, the parameter that is used is I squared T. If we take the integral of this that represents a sort of power, we take the integral of power, only if the integral of power reaches a certain limit, the system will blow. So in this case, you can use these delayed fuses, the T-type fuses, which have a small delay. How it is made, basically, it's a matter of power dissipation. Instead of having an isolated wire, you have a wire in sands. This is the La Sabbia inside the fuse. This transmits some of the power, so it takes longer for reaching the melting point. They are just simple tricks that the producer uses know for. I don't know if you are familiar with this kind of fuses. Those are the fuses inside the cars. The old car, now maybe they moved to something like this. I've never opened the box, but we're still like this. So when your stereo in the car is not working, probably there was a fuse like this that is blown. Okay. Yes, okay, something like this. These are for, yes, those are more for electronics. This is the kind for electronics, okay. And that's the fuse holder, this kind of, that's the kind. So in some equipment, you have this black screw. You can open it and change it, but first remove the plug from the wall, okay? Otherwise you touch, it's safe. And this is instead for some PCB, so it can be soldered on the PCB, and you can open the box and change the fuse. For instance, this you will find a lot of those in the alarm systems. In the box for alarm, it's filled with this stuff like this. So actually, these are curves that show you how long it takes before the fuse blows. Okay. You can study, that's more for electrical people. The fuses is nice, but the problem is that once it blows, you have to buy it. And usually the fuses blows on Saturday evening. So there's no chance for buying a new fuse on that. That's the reason why, at least in our houses, but also in modern equipment, there are things like this, magnetothermic thermal switches. Those are the switches that we are used to have in the houses. This is not my subject, but I like to tell you something because then we'll get to the degree and you never know how a switch in your house is made. So that's a shame, and so that's why I'm wasting time for doing this. Tell you this, okay. It is not correct that an electronic engineer does not know anything about this stuff. I'll try to explain in a simple way how it works. When we talk about thermal magnetic circuit breaker, so switch, basically this is a system that is able to control the current flowing through a line. You see here, this is the main switch. So there is simply a switch. The switch is controlled by those two elements. One means magnetic, the other one means thermic. How do they work? Basically, that's here says the line. So we put this switch in series with one of the two lines and two wires that we have on the wall. Okay, one is the neutral, so it's connected to ground more or less. The other is the live line. Okay, so la fase in Italian. So the line. And usually this is placed on the live line. Okay, so if you see here, basically, from that's the load, so our user. We take the line, and there is a switch. That is the switch that we see here. But we use the same current for doing two things. The first thing that we do is to letting the current flow through a coil, an electromagnet. Then we send the same current to a very small resistor that is here. What is the magnetic element? The magnetic element is sensitive to the instantaneous value of the current. If we overtake a current limit, this magnetic element, this coil, generates such a large magnetic field that attracts this metal stuff here. When we pull the stuff, we'll disengage the switch. There is a sort of something that when we move this in this way, this and open the switch, something like. So when you rearm the switch, you are doing this stuff again. You are rearming the system. That is done by a coil, and this is working instantaneously. So you can decide that your switch, for instance, must be open when you go over 16 amps, 32 amps, or so on. So you can decide which is the current, the threshold current for this magnet. That is instantaneous. So if you have a short circuit, it will open instantaneously. The second element is the resistor I told you. Actually, it's a bimetallic element. I don't know if you're familiar with the bimetallic element. Do you remember when you were very, very young, the Christmas tree had those flickering lights? Okay. Now they're made with LED and there is electronics inside them. But in the past, we used some kind of stuff, small plugs that were placed between the wall and the plug. Basically, a bimetallic system is something where you have two metals which are stuck close one to the other one. When you hit them, due to the fact that the metal have different thermal expansion, they bend like this, because one expands more, the other less. So if you hit this bimetallic stuff, it will bend. Bending, it will push the bar here, and it will disengage it.
Però non è istantaneo.
Non instantaneous. This is not instantaneous. No, it takes the integral of I squared t. So this will, it takes some time before it hits to the right point. If the overload is higher, it will be shorter in heating. But if you are just passing a bit the limit, it will take longer before it disengages. This is due to the fact that it protects against long overloading. Because a long overloading, for instance, can hit the wires in the walls. And you can destroy the isolation of the wires. If you, at home now, you have something like this. So basically, you know when you turn on the phone, the oven, the fridge, and okay, everything, the microwave, it will not disengage instantaneously. It takes 30 seconds and then you remain in the dark, okay? So that's the thermal effect of the, there are curves like this that tell you how much it can tolerate before it will switch off everything, okay? So in our circuits, both of them can be useful. In nice equipment, you have something like this or the miniaturized version of this in your equipment, because if there is an overload, it will wait for 30 seconds, then we'll switch off. In case you understand that something is wrong in the load, in this case, and so you can adjust the load and then rearm the system. And you don't have to wait 2 days before buying the fuse, okay? That's the reason why we use this kind of element in modern equipment. Non so, questa è una BB, 10, 15, 20 euro, something like that. Okay, that's it. Okay. Your colleague was asking, but at home I have something like this with a button to push. That's a different thing. It's so different that it's called a differential. Not just a joke. That's a differential switch that is used for a different situation. The differential switch, residual current differential, it's called, I forgot, is something that is used for protecting you from touching a wire and being killed by the current. How does it work? Well, it's quite easy. Basically, if you have an equipment connected to the wall, you have a current that is entering and the same current must be going out. If you touch one wire, a part of that current will flow through you to the ground. So the difference between the two currents will be different from zero. Actually, you see here, I have to try to salvavita, to expand it a bit. That's the neutral end line of your network, and that's the load. The current goes through a coil, the line current, also the neutral current, through another coil. The two coils are identical, but wound in opposite direction on the same toroidal nucleus. This takes the total flux is the difference by the fluxes created by the single windings. The single windings, top avvolgimenti, okay? So there is a third winding that is a sensing coil. If the flux is zero, there is nothing. If the flux is different from zero, means that you are touching one of the wires, okay? In this case, this kind of relay will disengage the two switches. Come?
Non ci sono problemi di induzione elettromagnetica in questo caso?
No, because this is a toroidal nucleus. The toroidal nucleus, in theory, confines the whole magnetic flux in the torus. Okay? Actually, you are not placing this torus close to the transformer or something. Okay? Okay. You will keep them quite apart. The button you push is this one. It generates, it's a resistance, so it generates a current leak from the supply to the neutral. So there is this current that passes here, but is not passing here. And so that's used for testing that the system is working. Usually the current here should be something between around 30 milliamps, because those systems usually are activated when the current difference is around 30 milliamps. 30 milliamps is at 30 volts is good enough for killing one person. So the system must be very fast in opening the circuit. Most of the time, instead, we have problems, not just because we touched, fortunately, but because maybe we poured some water on the load. Usually those loads are grounded. You see this box? That is connected to ground. So if for some instance there is a leakage of current from this wire to the chassis, to the metallic, the system will react. But that's true because if your system is not connected to ground and you touch something which has a short circuit between the chassis and the ground, that you will be killed. That's the reason why you must always connect to ground the chassis of equipments when there is a ground connection. Some equipment don't have the ground like this. No, this is ground, I think, yes. Not mine. This is a 3-wire, yes, connected with ground at the center. My power supply has only 2 wires. I can open it. We have batteries. So in this case, this has a double isolation inside. There is a symbol for like 2 squares. So there is a double isolation. You should not be killed. Anyway, okay. If you touch the computer, you will feel some discharge because it's not 100% isolated. Okay, so,
Quando porto ad esempio il gomito sul...
questo perché non ha...
attaccato però, senza caricare attaccato no.
No, c'è qualcosa che disperde.
C'è qualcosa
Che disperde la stampante, per esempio. Se c'è qualcosa collegato tramite la USB.
niente, c'è tutto il caricatore.
Il caricatore, sì. Quello. Se non ha la massa, se non ha il ground, quello disperde. No, okay, that's more complicated. Professor Vitale will show you that they create a sort of ground, just dividing the mains voltage into two parts with two small capacitors, and they connect the ground at the center, and that creates a dispersion of voltage. It's a very small current, but it's needed to fix the chassis of an equipment to fix the voltage. Otherwise, it's floating. That is even worse. Okay. When I bought this computer, they gave me this power supply, and I could feel that I had some dispersion. I called Sony. I said, "There is this. Oh, don't touch the computer. We'll send you a new power supply." So they sent me a new power supply with 3 wires. But I kept the old one, so now I have 2 power supply, one at home with these 3 wires, and this that I keep here at the university for this. See, because most of the PC are completely made of plastic. This one instead has some metal parts, and that's why I could feel the electricity. Okay. What is next? I don't remember. Okay. I don't know if you have a question also from home, or then I will talk to you about, you joined just today, okay, so I'll ask you some details about you, okay? Okay. What time is it now? Oh, 3:17. Do we want to stop for 5 minutes? Okay, so we can, okay. So also from home, then we'll start with this part. Okay.
A dopo, professore.
Ci sentiamo tra qualche minuto, ok? Tranne che, have you a question? I can't hear you. Okay. Okay, see you in a while. Okay. Okay, so we are back. Are you ready? How much do we have left? Half an hour. Okay, so once that we have seen all those nice circuits, I would like to show you something a bit more advanced. Don't be worried. This is basically a basic and old integrated circuit. We are talking something that was created in the 70s of the last century. So it's almost 50 years old. That is one of the first integrated circuits for creating a power supply, an integrated power supply. So a single chip which contains 16 transistors, at least, and allows to make a whole power supply with very nice performances using only one chip and some other components outside. I like to show this IC, integrated circuit, because it's very basic, but also a lot of tricks about integrated electronics. If you consider the name ME-A723, it's not very different from the 741, that is the operational amplifier. Actually, if you compare the two chips, the standard operational amplifier, the ME-A741, and this one, 723, they are very similar because they were made by the same generation of designers. So the same key points were in both devices. Then we'll see the performances. First, I want to show you which are the tricks that the designer used for creating this circuit here. Don't be afraid of the circuit that it seems to be too complicated. Well, it's a bit complicated, but you will discover that you know most of what is drawn here. First of all, I want to show the block diagram so that we can recognize the different blocks later. The block diagrams is this one. We can start from the output. This is a complete series pass power supply, including feedback. So we have a series pass transistor that is the main transistor that we place in series with our between the source and the load. So if we go back, I'm talking about this transistor here. In this chip, we have only one transistor. We don't have the Darlington. That's the reason why the output current, the maximum output current, is limited to 150 milliamps. But if we want to improve the performances, we just can put a second high power transistor in cascade, and we get a Darlington. A part of the first part of the transistor is inside, the second part is outside. Well, actually, I am not saying the truth. Because even if this block diagram considers a series pass transistor, if you look at the real devices, you see that we are talking about Q15. But inside the chip, there is already a first transistor. So there is already a Darlington inside. Here is shown like a single transistor. The other point is that due to the limitation of the packaging, we must limit the current to 100 milliamps, otherwise we are going to overheat the chip. So we prefer to have a third transistor. So we have a Darlington with 3 transistors in cascade, but the external transistor can be fixed on big heat sinks with fan, and so we are not heating the chip. That's why they prefer to limit the current to a minimum here, and then this large transistor, power transistor, is made somewhere else. Okay. Actually, you can connect it with wires, the chip to the transistor. It is in the outside of the box or something like that. And then you see here, there is this current limiter transistor that is connected with a collector on the base of the output transistor. This means that you are available this transistor for making a constant current limitation, short circuit protection, or a fallback protection. They give you the two wires, the base and the emitter, because you have to change the schematics, and that part of the schematic is made outside, so that part of the circuit. So if you want to only have a constant current limitation, you will put a shunt sense resistor between base and emitter. If you want to make a fallback, you need the sense resistance plus the voltage divider connected somewhere else. Don't look at this diode. This is made for some particular applications. And now we go back on this part. Basically, what we have here is something that we saw in the past. We have a Zener diode that is controlled with a constant current generator. If you remember, one way to have a fixed, a stable voltage from a Zener diode is controlling it through a constant current generator. If they keep the current constant, the system will keep its voltage fixed. We are not considering the thermal variation. What I'm considering are the variation in the supply voltage. If you remember, when you have a Zener diode and a resistor on top, the voltage on the Zener diode depends on the supply voltage. So one way to reduce the dependence of the output voltage from the supply voltage is to place a current generator in series with the Zener diode. And that's it. This is interesting. This is, well, a JFET. It's a FET, feed-FET transistor, in a particular configuration where you keep constant the gate to source voltage. Why is that possible? Because if you remember the characteristic of a field-effect transistor, this is a JFET, but for the MOSFET is the same. They are basically quadratic in the triode zone, but then they become flat. Flat means that if you keep the MOSFET at a constant voltage to gate to source voltage, and you are in the saturation zone, more or less the current is constant. It's not dependent on the supply voltage, on the what is that? Drain to source voltage. Well, actually, there is some bending due to the dynamic resistance, but that's very limited. So basically, we are fixing the characteristic with a 0-volt gate to source voltage. So the BGS is 0 volt. This means that we need a device with a negative threshold voltage. Negative threshold voltage is typical for JFETs or for depletion MOSFET. So in modern design, we could use a depletion MOSFET. This is an old design. I use the JFET. That's not bad, because if you see the circuit is completely a bipolar circuit. So all the devices are bipolar. They have no MOSFET. The process for making a MOSFET is very different from the process for making a bipolar transistor. So if you choose one technology, you will probably use the same technology throughout the layout. When we have a transistor, it means that we will need 3 layers for making PNP doping, for instance, or NPN dopings. The JFET can be done with the same process. A MOSFET needs something different, because you must, for instance, deposit the gate isolation layer and so on. So the silicon dioxide for making the gate. So usually we don't want to mix different processes, because it means using more masks and means increasing the price, increasing the cost. So in this circuit, actually, they use the JFET. So the JFET is basically used as a constant current generator, which does not depend on the supply voltage. This is so important because if you see which is the maximum supply voltage, that's 40 volts. But the minimum can be something like 10 volts or even less. So this chip is able to generate, to be used with the supply voltage between 10 and 40 volts. This is a very large voltage variation. We can decide the output voltage of this power supply. And so we must design everything in order to tolerate such a large voltage variation without changing the characteristics. That's why we use definitely a constant current source for powering this Zener diode here. Then it... Come? No, that's a Zener diode. No, the S is the other way. Okay, your colleague was saying that it looks like a...
Se guarda anche in quello in basso a destra, quello è uno Zener. Perché la forma di Z?
It's the same. It's the same. The Schottky diode has these curls that go around for a while. I riccioli si chiudono. This is not a Schottky, this is a Zener.
Il professore Armani mi ricordo in una lezione, mi è rimasto impresso, perché mi disse che quando ha la forma di Z vuol dire che è un Zener, quando invece ha la forma di S sempre dritto è una Schottky.
This is a Zener. Okay, so now I understand. Okay, but usually the Schottky is something which goes like this thing. It's more close, it's like a curve of the hair. A più ricciolo, diciamo. Okay, so basically this, okay, what is that? This part of the circuit is something that generates very accurately 6.2 volts. 6.2, it's a bit strange because it has a thermal dependence on the temperature. So the voltage is dependent on the temperature. But this diode here is used for generating a fixed current in this current mirror here. Remember current mirror? Current mirror, you have two transistors, where one, the master is connected as a diode, so the base and the collector are short-circuited. We input the current through this resistor here, and the second transistor reproduces the same current. But actually, here, it is not a simple current mirror, but it's something between a current mirror and a Widlar current mirror, because we have a large resistor on the emitter of Q3. Here, here, and here. We are using the same VB for all the three transistors, and so we have three current sources which have different, we are sourcing different currents because they have different emitter resistors. Okay. Actually, someone could say, why are they using this R1 resistor on the emitter also of the master transistor? Well, I can tell you that this resistor can be used for dividing the currents in a different way. You have 1 degree of freedom more to decide how to divide the current. Also, in some way, it gives you some negative feedback, so stabilizes the transistor Q1. They say also that even if this Zener diode has a positive thermal coefficient, this combination was able to balance the thermal coefficient. So we trust him. Okay. In this way, basically the currents generated by each of those transistors is quite stable in terms of temperature. So we can trust it. Okay. I don't want to spend more time. Otherwise, we should make simulation, calculation, but that's not the purpose of this moment. Okay. Now, if you take a look at this circuit here, is it something that we have already seen or not? Yes, this is a constant current voltage reference. Because basically we have, again, a Zener diode that is in series with this SC resistance, we call it the sensor resistance. This voltage is powering the transistor Q8 that closes the loop with the transistor QA and Q5 that are sort of Darlington configuration. So basically we have a constant current that is injected by transistor Q3 that is regulated by transistor Q6 depending on the feedback that it gets from the R8 resistance. So here, once more, we have a constant voltage This constant voltage is used as the master reference for the circuit. So actually the system is giving you a VREF output. The peculiarity of this circuit is that actually there are a lot of pins that bring out some particular signals. This is a very versatile circuit. So it gives you a lot of pins and you can decide what configuration you can do. Believe it or not, you can make also a switching power supply using this chip. Because they gave you all the outputs and inputs of the circuit. Okay, so basically what we have here, as I told you, is a constant current voltage, reference voltage circuit. Then we have this group here. Okay, that's a differential amplifier. The differential amplifier is used as the error amplifier. So at the moment with this VREF we are here, they show a sort of Zener compensated Zener diode plus an amplifier. The amplifier basically is this feedback system here. This means that actually from the VREF you are able to take also some current, just a few milliamps. Okay, you see here 15 milliamps. You can take the 15 milliamps from the VREF voltage, so from 0 to 15 milliamps. And in this case, they will tell you that the reference voltage will be quite fixed, around 7.15. Remember that we said that usually the output is around 7 volts, with this plus minus 0.2 volts. Well, okay, exactly. So this is the reference voltage that the system is able to give you. It says it's 7.15 plus minus 0.2, but this is not a variation in terms of depending what is the temperature, depending on the load. No, this is a variation just, this variation between different chips with the same name. But once you buy a chip, it has a very fixed voltage. And look at this, the stability, 0.015% over Celsius degree. So it's extremely stable. Maybe we'll measure 7.18 volts. Okay, but once you have that voltage, because the voltage has to do with the chip, that single chip that you bought, it's quite stable. So it's very well compensated. So this is a very nice device. What are those? So we have here basically the differential amplifier that is used as an error amplifier. This is a very accurate amplifier because it has a nice current source on the meter. Also, what are those ones? Do you remember when we studied the current mirrors that we studied a system with 3 transistors? That is the transistor which compensates the current taken by the bases of the 2 transistors. So the Q7 is the current source. The Q10 could be the diode connected transistor, but just because we want just perfectly mirror the 2 currents, we are using this transistor for compensating the currents. But then we study also Wilson current mirror, and the Whittler. The Whittler we have also already seen it here. No, where is it? Here. Okay, basically. So we are remembering things that we studied last year. By the way, I'm afraid that some of the students that are not from Palermo may be not so familiar with current mirrors, differential amplifiers. I will be pleased if you tell me, Professor, I don't remember a lot about this stuff, because I can try to help you to explain you something, okay? But please tell me now that you are not familiar with those circuits, because I can try to give you some material about those subjects. You should do that now, because if you do that when we are at the exam, you know that maybe I will not be so polite with you. So please tell me now that you have a problem on those circuits. I will try to do my best for helping you, okay? So please, if you don't understand something, tell me now. Okay, so basically now we have this differential amplifier. We are interested in taking the output from the collector transistor Q12, and for increasing the gain, we are using an active load here. The active load is made by the same current source. So we can maximize the gain of this differential amplifier. So basically, this is the equivalent schematic that we can use for designing the circuit. So we have basically two wires for positive and negative power supply, voltage reference that is fixed, but then we have fully available the two inputs of the error amplifier, and any other connection. Maybe now it's a bit late, because I would like then to show you how this chip can be used for making real power supplies. So starting from this block diagram here, you will find a lot of possible configurations that are very interesting for developing power supplies. There is a one with the low voltage, low output voltage, the other one for high output voltage. You see here external transistor, NPN transistor, but you can also do something with the NPN transistor if you want. Or you can implement the fallback system. So I would like to spend with you a bit more time, maybe next Tuesday morning, and try to have a look at these chips. What is this? I don't know if you ever used this kind of chips. This is a very popular chip. It's a voltage power supply. The 7800 or XX series. If you are interested only in having a very good power supply with a fixed voltage, you can buy one of those chips that cost nothing. They have three wires. One is the input, the other one is the output and ground. You just add a few capacitors, and that's it. Basically, the inside is the same as the M723. They are derived from that one. This chip costs, say, 50 cents or even less. It depends on how many of them you buy. And you can have a lot of fixed voltages. You see? If you want the 7805 is 5 volt. This is very popular, for instance, for all digital circuits. If you have a digital circuit working at 5 volts, use this one. C means plastic container or something like that. So there you can buy different configurations. See, the typical one is this one, the TO220. That's the typical. They look like a transistor, a power transistor. Yeah. This is maybe cheaper, is more plastic than metal. This is a big one, which can give you up to 5 amps. So this needs a larger dissipator. And this is a surface mount chip. So you can, there are even more. This is an old data sheet. Now they've increased the number of possible packages. So this is very popular. And also it has inside a lot of protection. Short circuit protection, overheating protection. So for destroying one of these chips, you must be very hard, just with the hammer. Okay. Or the other way to destroy one chip is to invert output and input. In that case, we will destroy it. Otherwise, they are very well protected, and they will never die. Okay? So, but I prefer to have a bit more time to spend with you discussing those chips. Again, you can invent a lot of possible configurations of those chips. So it's quite unlikely that you will design a power supply, but you will probably use one of those chips. There are some particular applications where you are forced to design your own power supply. So that's why I'm teaching you what is inside the power supply, but also what you can buy as a power supply, if it's already made. This one, LM370, is the same as before, but this allows you to change the output voltage. It's again a 3-terminal chip. So give me more time, I will show you something more about this. Because those are very popular, and you must know them, because they're used everywhere. Okay. Okay, at this point, I will stop here the classroom, and see you on Tuesday, at least for this part, okay? Have a nice weekend to everybody, okay? Bye. Arrivederci, bye bye.
Thank you.
Bye.
Arrivederci.